Hello, my name is Arthur Wang. This is my Lab 1 constant velocity lab report. So for the experiment, we will observe the motion of some object that is moving at the same speed without changing direction. Then, we will construct an observed position versus time graph through the use of tracker to analyze the video. And then, we will then construct a predicted position versus time graph by making a computational model that applies the concept of Newton's second law. Finally, we will compare the observed and predicted position versus time graphs. Alright, the subject of my experiment. My experiment examines the position versus time function of a ball rolling on a flat plane at a seemingly constant speed. There seems to be either no net force acting upon the ball as its movement is constant, but there could still be equal and opposite forces acting upon the ball that would still result in a constant speed. That's the video. The ball is moving on a completely flat plane, and it shows the tracker points as the ball rolls. And it seems to be at a constant speed. Okay, for Newton's second law, V final equals V initial plus F net divided by mass times delta T. Alright, so at the start of this lab, it's specified that the speed has to be constant and there's no change in direction, which means that the velocity must also be constant. Therefore, V initial and V final, if they were to be the same thing, you could technically just cancel them out from the equation. They are basically irrelevant. So the F net must also be 0 because the velocity must stay constant, which means that F net has to be 0 to ensure that there's no acceleration. And mass is arbitrary because it is a constant. Applying Newton's second law. My computational model code applies Newton's second law in updating the position. For this lab, F net and mass are arbitrary for the reasons stated before, stemming from the speed having to be constant. We don't need to update the velocity because we can assume that the velocity will not change based on the criteria laid out by this lab. Down in the bottom right, we can see that ball.position equals ball.position plus ball.velocity times delta t. This is just a modified version of the Newton's second law formula on the previous slide, with the parts that we don't need actually removed. The time interval is chosen based on how long the tracker clip was, just so that I could have more consistent graphs that I can put next to each other. Alright, so comparing the results. So the red line is the computational model, and blue is the tracker data. So what we would assume to be true from the ball, if it were completely, or if it's moving at a constant speed, we would assume that my data should also technically be a straight line. However, because you have to click frame by frame on the exact same position on the ball, it's not completely straight due to user error. But it does follow the computational model's line quite closely. You can see it starts above due to the alignment of the axes, which is a little bit off. But it does start and end very near to the computational model, and it only fluctuates above and below based on minor errors made by me clicking frame by frame. Okay, so comparing the results continued. On the right, we can see the visualization in the graphs made by GlowScript for the model. Okay, so the main assumptions that we can make for the computational model were that velocity would be constant because the constant speed criteria, and the ball would move completely in the x direction only. Okay, so the constant velocity is assumed due to the criteria, and the ball moving completely in the x direction is only assumed from examination of the video that I analyzed with tracker, where the ball is literally just rolling sideways or to the right on a completely flat plane, or seemingly. Again, the tracker curve could technically have followed the computational model's line of best fit far closer, but the limitations of trying to click an identical position on the ball per frame is inherent with the small fluctuations above and below the curve on the previous slide. So what if? Flipping the axes. So at the start of this experiment for tracker, we chose which axes to correspond to which direction of movement. So I chose initially the ball moving right, corresponding it to it moving in the plus x direction, but an axis flip would mean it would technically move in the negative x direction, even if the ball is still moving right, because if the axes were flipped, the curve would maintain its shape, but with sign changes applied to the data points, and therefore the velocities and positions would become negative rather than positive as the graph increases in the first quadrant. So what does it mean? Your observations can be predicted well by your computational model when you set the net force equal to 0 in your model. Is it possible for you to say how many pushes and pulls, i.e. how many forces, are added together to give 0 net force in the case that you observed? Well, in the scenario observed in the video, it's not really possible to say exactly how many pushes and pulls are added together to give 0 net force, because we simply do not have enough context to the scenario, but we can only make assumptions about the scenario based on our observations of it, and the corresponding mostly straight graph derived from the tracker data points. Thank you.